topic of today's meeting, of today's lecture, is the continuation of the preparation for Hartree-Fock method. And I'm going to review administrative part of the of our course, although there are not too many people in the audience, but I hope you'll be able to share it through tape recording. So please keep working on the homeworks that have been already distributed. And in a week from now, on Tuesday, February 26th, we will have very important session in the basement of Arts and Science. So please stop by. And if you would like to come today, it is also possible. I'm not in the city, but Vinatini Balasubramanian, I left the keys with her, and she is able to come down, open the room, so you can keep working on the projects. And on one Thursday from now, on February 28th, we will do oral presentations. And on the next slide, I'm briefly reviewing which assignments which subjects we can consider to present. Okay, and here's a little overview of subjects that I'm going to briefly cover. So I will introduce so-called variational principle, and then I'll talk a little how one gets molecular orbitals as a superposition of atomic orbitals, and why it is important as a part of Hartree-Fock theory. And then I will review the sequence of calculations going connected to each other. So from atomic orbitals to coefficients to molecular orbitals to Slater Determinant to total energy, which is a procedure, a routine of the Hartree-Fock theory. Okay, let me see how do I navigate through the next slide. Okay, so here's the possible list of subjects, and it is not final. If you have an idea that you want to do another subject, or you're not happy with what I suggest, you're free to modify, to change. So it is suggested to have 8 subjects, and we did cover the subject number 5 and number 6 when we met last time. So it is how to prepare Gaussian input and how to analyze Gaussian output, right? You have practiced it. And we are definitely, I promise, we are going to cover the subject number 3 of how to do molecular orbitals with Gaussian and Gauss-U software. The number 1 and number 2 are a little bit more academic, but they're important to make our short presentation session complete. And the numbers 7 and 8 are of practical importance for research project. So I will cover them on next Tuesday in the lab if you have time. So please review names near the subjects and let me know if it looks okay for you. For the next slide, we are looking towards finding the solution of electronic structure, of only electronic part of molecular Schrödinger equation. And for electronic part, we already know how to construct many electron functions. We know the principle of Slater Determinant. And we also were briefly discussing that there is a trick as a part of Hartree-Fock theory that one can build a set of 1 electron orbitals and use them as a building blocks for many electron wave functions. But when I listen to myself, there appears a little confusion. There are hydrogenic orbitals on atoms, and there are some orbitals, 1 electron orbitals used for Slater Determinant. So they are different. There are atomic and molecular orbitals. And let's discuss it a little bit today. Okay? So I'm going to introduce so-called variational principle. And this principle is an alternative to the eigenvalue, eigenstate problem. So let's assume that we do have big wave function for the if you have Schrödinger, if you do have Hamiltonian operator, there is a procedure how to extract total energy of a system based on the wave function. So this little formula is nothing but typical, standard expectation value formula. So you have bra and cat for wave function. Here we assume wave function of many electrons. Here is the precise many electron Hamiltonian. And in the denominator, we do have normalization factor. So there is a procedure that connects wave function, if it is known, and energy. And here is a little bit philosophical, a little bit suppose that wave function is something that we can tweak, we can change. And the question is, how does the total energy changes if one is going to modify the wave function? So one can take the wave function for ground state and then make a little modifications, maybe change the probability amplitude that electron appears in one place or electron hole pair appears in other place, some little variations. And we are posing a question, how the variation of the wave function affects the energy. I'm going to go to next slide. And here is a little illustration. So the first cartoon is, let's say, ground state wave function. Second cartoon is a little addition, which may have a little bit here, a little bit there, but something small and random. And if one adds them together, there will be some more complicated wave function. And here I'm showing everything in one dimension. So the question is how the energy will change if we modify the wave function. So there is a statement, there is a theorem that for each molecule, one can find such many electron wave function that will correspond to a ground state, to equilibrium, lowest possible electronic state. But if it is true, then any wave function which is a little bit different, this delta symbols means small variation of the wave function, will bring the total energy of the system away from the minimum. And this is a very simple but helpful and critically important philosophical concept. So varying, modifying wave function away from ground state wave function will bring us away from the minimum. Energy will increase. I'm going to the next slide. And here is the mathematical reformulation of this idea. So in this, in the left part of the inequality, we have an expectation value of Hamiltonian operator. So bra operator cat. So this is a total energy, total electronic energy that we later use for geometry optimization as a part of the whole system. Now, if you take our wave function and modify it, no matter how, if you go away from the ideal ground state, then we take this modified wave function, bra and cat, and do use it to compute the total energy, the expectation value of total energy. So there is a statement, there is a theorem, then for any change of ground state wave function, the total energy will be bigger than ground state energy. So it is more mathematical approach to look on these things, but it is one of the cornerstones for Hartree-Fock theory and for several other theories used to find electronic structure. So if we are lazy, or alternatively, if the calculation of electronic structure is too heavy, too complicated, takes too much numerical resources, we may imagine, I'm not telling that we are going to do it, but we can imagine a computer doing the following simple routine: generating wave function by random numbers, something random, unknown, computing total energy for random wave function, record it into the list, and do repeat it again, again, and again. And then we order this list according to ascending or descending energies, and select the record that corresponds to minimal energy. Then this minimal energy will be actual and total energy of the system, and this wave function, which can be obtained just randomly, will more or less correspond to the actual wave function of the system. We are not going to do it. It is just an example what one could do. And this is an alternative of solving eigenstate problem, because in multidimensional, for multidimensional wave functions, exact solution of electronic problem, exact diagonalization of Hamiltonian is not possible. It would take longer time than humankind, and maybe just everything exists. It will take astronomically long time. Okay, so I just verbalize it here. So minimize list and find correct energy. So by trying different variations and another variation and another variation, you can go downhill to the lowest minimum. Okay. There should be some more rigorous, more reasonable way to find many electron wave function. I'm going to go to the next slide. So we already know that many electron wave function is composed of single electron orbitals. And what we are going to do is to pose a problem, pose a mathematical problem, establish a new philosophy that on one hand we have a routine how to compose multi-electron wave function out of single electron wave functions. But we do not know which single electron wave functions to have. And we are going to introduce the concept of those unknown orbitals. And we are going to proclaim that by selecting correct set of one electronic orbitals, one can compose very good, very high quality, very precise many electron wave function. And the main thing that we are going to modify and we are going to look for in a technical way is a set of one electron orbitals. And you already know that they are called molecular orbitals. And they are even they were used even without Hartree-Fock theory as an independent philosophical concept. Okay, it is a verbalization of this idea. So the way how these orbitals are built will be left for the next lecture. But now let's discuss once again the bigger picture, the connection between atomic orbitals, molecular orbitals, and the whole many electron wave function. Okay? I'm going to go to the next slide. So we need a set of molecular orbitals to build bigger many electron wave function. So if we do have set of these MO molecular orbitals, if it is a good set, then it will provide optimal multi-electron wave function, and the optimal multi-electron wave function will provide minimum of the total energy. So those molecular orbitals can be composed as superposition, as an overlap of these chi functions. So these chi functions with different coefficients. So this simple equation presents the molecular orbital. MO stands for molecular orbital. J stands for index, because there are several of those. And here we do have a summation along the letter A stands for all quantum numbers, and letter I capital stands for all ions. So the atomic orbitals are defined for each ion, and this R lowercase minus R uppercase means that atomic orbitals are existing around each ion, right? So there are ions, there are atomic orbitals around each ion, and then they are taken with different weight coefficients. So this C, A, J are weight coefficients, and if we add together several atomic orbitals in different proportions, then we get this magic object called molecular orbital that is later used to build multi-electron wave function. And it is what we are going to learn how to plot with Gauss-U software when we meet next Tuesday in the lab. Okay? So those are atomic orbitals, those are position of ions, and those are CR expansion coefficients. Okay, I'm going to the next slide. So here is a little overview of the procedure. How do we get from atomic model, from positions of ions, to the total energy? So after we get model of a molecule, we get positions of each ion. We are selecting, or someone helping us, to get atomic orbitals, which are typically referred to as letter chi, which looks like X. Then, by some nice procedure, we are guessing, or we are finding set of expansion coefficients. And by merging together atomic orbitals and expansion coefficients, we are getting molecular orbitals. And then, through Slater Determinant procedure, molecular orbitals are constructed together into many electron wave function. And then, after we know many electron wave function, we are finding total energy. And we, the Gaussian software can perform Hartree-Fock calculation. And we have seen in the lab that we can report total energy for each atomic model. So it is just illustration what we were doing last time. Atomic orbitals, expansion coefficients, molecular orbitals, multi-electron wave function, and then total energy. So in this procedure, in this set of arrows, we need to change anything we can in order to minimize the total energy. So the goal is to minimize the total energy. And I'm going to the next slide. And here, let me ask you a little question. So please try to answer out loud, or write down your guess in your notebook, or let's analyze together. In this list, atomic orbitals, coefficients, molecular orbitals, wave functions, and total energy, what can we change as humans, or what a computer that serves us can change in order to minimize total energy? So please do not hesitate. Can we change atomic orbitals? What do you think? Probably not. Can we change expansion coefficients? Switch on the microphone if you want to, if you're going to speak. So, do you think we can change expansion coefficients? Probably yes. I do not hear SDSU. Okay. Okay. So, if we change expansion coefficients, then we automatically change molecular orbitals. Very good. Then, for this part, for wave function, we are not changing it ourselves because the procedure of how to construct wave function is already determined. And the procedure how we get total energy out of wave function is already also determined. So we do not have an opportunity to modify it. So the only thing that we can change are those expansion coefficients. Yes, yes, right. So the whole Hartree-Fock theory is a mathematical problem of finding the correct expansion coefficients. The overall construction is much more simple. It is much more simple than usual Schrödinger equation, but practically, the problem is reduced to finding those expansion coefficients. I'm going to the next slide. So we have yes for expansion coefficients and no for other things. Okay. So if we do believe in, I'm going to the next slide. If we do believe in the variational principle, then we can.
The conference will automatically end in 5 minutes.
Okay. So we can believe that by modifying expansion coefficients, by tweaking the expansion coefficients, we can change the whole line, whole procedure of getting total energy. And by trying different set of those expansion coefficients, we can get minimal energy. Okay?
Okay.
So if we get those C coefficients, finally we can get correct, more or less correct multi-electron wave functions, possibly lowest energy. So the simplest thing would be just guess them randomly and try any possibility. It is already possible, and this principle of trying random realizations is used in so-called Monte Carlo, quantum Monte Carlo procedure. But here we are following Hartree-Fock, who developed a smart way to guess those coefficients and improve them in a several incremental cycle. So there is, and this, since this procedure is also helping to find the average potential that all but one electrons apply to a single electron. Because of this reason, this procedure is called Hartree-Fock self-consistent procedure. Because electrons change, the field is changing, electrons are changing, field is changing, and finally everything converges. So this procedure that we are not going to cover today, but I'm announcing it, this procedure, this Hartree-Fock procedure is very similar, very analogous to one electron Schrödinger equation. And by solving this equation, which is similar to Schrödinger equation, one is obtaining these C coefficients for molecular orbitals. So we will be formulating questions how to find those C coefficients. Now I'm going to the next slide. So procedure, we are getting the coefficients and molecular orbitals. And as we go, we will find that molecular orbitals are helpful by themselves. For example, they can show whether they're looking differently for bound and disconnected species, they can prompt physical properties, some optical properties, some chemical properties, and they are right tools to construct multi-electron wave functions. So in order to find them, in order to find those expansion coefficient molecular orbitals, one is solving for eigenvalue problem, but instead of Hamiltonian operator, which is used for educational purpose for any Schrödinger equation, and here we do have molecular Hamiltonian for a bigger molecule, one uses so-called Fock operators. So Fock, because it is after the person who was devising, establishing this operator, and the difference that it is one electron operator, but it does contain some features of multi-electron interaction. And therefore, the letter F is used for. So you recognize the difference and be sure that we are working with Hartree-Fock method. I'm going to the next slide. So in the next lecture on Thursday, I'm going to be brief today and finish in a couple of minutes. So on the next lecture, I'm going to cover the subject, how to carefully construct these Fock operators. And through solving the eigenvalue problem with Fock operator, one is getting expansion coefficients and molecular orbitals.
The conference will automatically end in 30 seconds.
So in practice, Fock equation is solved several times. Total energy is found several times. This procedure is repeated iteratively, but in a very few iterations, like 10, 20, one is getting very good results for total energy and for multi-electron wave function. So with this, I'm ending this lecture.
Conference ending. Goodbye.
So if you would like to ask some questions, I'm online and we'll be happy to answer them right now. So if not, you don't have questions right now?
Okay. Today we have the practicals. Yes, Vino will come.
Please?
Vino will come.
Yes,
Today evening we have the practical. Yes, I'll come.
Very good. Did you talk to Shiva? Oh, not Shiva, Vinatini. Vino?
Yes, I talked. Yesterday I
Okay,
talked.
she will open.
Yes.
Okay, very good. Very good. And I have already put this lecture on the D2L.
Okay, thank you.
If you like, we'll send it as an email.
Okay.
So, okay. Then thank you very much. And as an entertainment show.
I couldn't hear your voice.
Oh, that's not fair.
It was entertainment. Okay, then I will be checking emails regularly and happy to answer any questions.
Okay.
With this, I suggest we have our meeting dismissed.
Okay, thank you.
Okay, thank you very much. Have a nice day.
Okay. Excuse me, USD, can you hear me?
I can hear you.
Do we have lab today?
Yes, but he was not come, but he handed over the key with one of our colleague, Vinodini.
Okay, what's your name? Can I get your name? I am Sushil.
Shelton.
Can I get your number maybe? Actually, we're having problem, you know, we don't have any instruction for lab, nobody.
Sorry, at the moment I don't have a phone here, but please give your number, then I can call from Vino phone.
Oh, okay, can I give you my number?
Yes, sure.
Okay, it's 903
903
467
467
7300.
7300.
Yeah, my name is Sushil, Sushil.
Okay. Okay, thank you. I think most probably I'll call around 6 o'clock.
Okay, no problem. Thank you so much.
Okay, thank you.
Really. Bye.